Hello, my name is Tom Hartley, and along with my supervisors, Kirill Sidorov, Christopher Willis, and David Marshall, we would like to present our work, SWAG-V, Explanations for Video Using Superpixels Weighted by Average Gradient. This work was done at Cardiff University with sponsorship from BAE Systems and the EPSRC. Explanation techniques for convolutional neural networks are typically designed for networks which use an image as an input. Networks which use video inputs for tasks such as action recognition often have different architectures. However, often we see that techniques designed for image-based networks, such as Grad-CAM, are used with these networks. This is problematic, as one property of common video-based networks such as C3D, I3D, or R2+1D is that the temporal element of an input is compressed as it passes through the network. For a 16-frame input, this results in Grad-CAM explanations being created for activation maps of only 2 frames, and then being resized using interpolation back to the original 16 frames. A technique was introduced at WACV 21 called SWAG, Superpixels Weighted by Average Gradients. SWAG creates superpixels using the input image and then uses backpropagated gradients to weight the superpixels to show how important the underlying region is to the network's prediction. We proposed that SWAG could be modified to create accurate explanations for videos too. We therefore propose SWAG for video, or SWAG-V. We take a multi-frame input video and create a set of superpixels which incorporate a region of the video both spatially and temporally. We then generate a gradient explanation and use these values to weight each superpixel. Through experimentation, we found that using guided backpropagation as the gradient explanation method gave the most accurate SWAG-V explanations. An example frame from our approach is shown at the bottom. Here we see an input frame and the gradients and superpixels created for this frame. The superpixels are then weighted using the gradients to produce the explanation on the right. SWAG-V works well for video inputs, as the superpixels and gradients are created at the same temporal resolution as the original input. This allows the explanations to both align spatially and temporally. A question that quickly arises is how many superpixels is an appropriate amount? Too many or too few, and the explanation could be confusing or inaccurate. To answer this, we sweep through a range of superpixels and use the combined insertion and deletion accuracy metrics to determine where the optimal number of superpixels is. This is the chart shown to the side. Here, a lower AUC score is better. We found that 120 superpixels was the amount that gave the best combined insertion and deletion scores. Here, we show alternating frames of an example clip from the Kinetics 400 class ski slalom. We can see how a method such as Saliency Tubes, which is similar to Grad-CAM, is both spatially and temporally coarse. 3D external perturbations are able to better locate and follow the action, but are still spatially coarse. Our SWAG-V example is better able to follow both the action through time and more accurately identify the skier performing the action in the frames. Further examples are available in the paper and supplementary materials. We measured the local accuracy of comparable methods using the insertion and deletion metric. We found that the insertion metric favored spatially coarse methods, whilst the deletion metric favored very fine explanations. As our method was designed to give a balance between both the insertion and deletion metrics, it performs comparatively well in both. In addition to accuracy, we also measured how well the explanations are able to locate the action. We used a 20-class subset of UCF 101, which contains bounding box data for the actions being performed. If the explanation overlapped with the bounding box by a certain amount, then it suggests that a given technique is able to locate the action. As shown in the table of results, SWAG-V outperformed all the other techniques we compared against. Creating and weighting superpixels for SWAG-V introduces an element of inefficiency. However, we found this was only a small increase on techniques such as Saliency Tubes or Grad-CAM, and much faster than EP3D. In summary, we show that SWAG-V is a useful technique for explaining the prediction of networks which take video as an input. It performs well in local accuracy and localization metrics, with only a small computational overhead added. Further examples and discussion are available in the papers and supplementary material. Thank you for watching, and we'd be happy to take any questions you might have.